October 14th, 1943, 32,000 feet above Schweinfurt, Germany. Oberleutnant Egon Meyer pushed his Messerschmitt Bf-109G6 into a climbing attack, the aircraft struggling against thin air that barely sustained flight. His engine screamed at maximum power, the supercharger laboring to compress enough oxygen for combustion. At 28,000 feet, his rate of climb had degraded to 500 feet per minute. At 29,000 feet, it dropped to 200 feet per minute. At 30,000 feet, his aircraft wallowed at the edge of its performance envelope. Controls mushy, engine temperature redlining, speed bleeding away despite full throttle. Above him, seemingly oblivious to the altitude that was suffocating his fighter, a formation of B-17 flying fortresses cruised at 32,000 feet, their right Cyclone engines running smoothly, their formations tight and precise. The bombers flew as if the altitude was comfortable, making coordinated turns, maintaining formation integrity, their defensive gunners scanning for fighters that couldn't reach them. Meyer pulled his stick back desperately, trying to climb those final 2,000 feet, watching his airspeed indicator drop below 180 meter pitch, feeling his aircraft begin to buffet as it approached stall speed. He had two choices: level off and watch the bombers fly serenely overhead, or continue climbing and stall, spinning helplessly toward Earth while the Americans completed their mission unmolested. He leveled off, gasping for oxygen even through his mask, his vision tunneling from hypoxia and exertion. His radio crackled with similar reports from across the formation. German fighters that had terrorized Allied bombers for 2 years found themselves unable to reach the enemy. The Americans had somehow achieved sustained operations at altitudes the Germans had calculated were impossible for heavy bombers. What none of the German pilots understood as they watched the contrails of unreachable fortresses was that they were witnessing the practical application of an American engineering solution that had been dismissed by German technical intelligence as theoretically unsound, mechanically unreliable, and operationally impractical. The turbocharger, a device that used exhaust gases to compress intake air and maintain sea-level engine power at altitude, had transformed the B-17 from a competent bomber into an aircraft that could operate in atmospheric conditions where German fighters could barely fly. The mathematics of altitude advantage were being written not in aerodynamic formulas, but in the thermodynamic efficiency of turbines spinning at 20,000 RPM, compressing thin, stratospheric air into breathable density for engines that powered bombers beyond the reach of German interception. The impossible had become routine, and the device that German engineers had abandoned as too complex was about to change the strategic balance over Europe. The story of how exhaust-driven superchargers transformed American heavy bombers begins not with war, but with the peacetime quest for altitude records and the recognition that engine power was fundamentally limited by atmospheric pressure. The problem was as old as aviation itself. Internal combustion engines required oxygen to burn fuel. As aircraft climbed to higher altitudes, atmospheric pressure decreased. Less pressure meant less oxygen per unit volume of air. Less oxygen meant incomplete combustion, reduced power output, and eventually altitude where the engine couldn't produce enough power to sustain flight. By the 1920s, aircraft designers understood this limitation created a ceiling for both fighter and bomber operations. Reciprocating engines lost approximately 3% of their power for every 1,000 feet of altitude gained. An engine producing 1,000 horsepower at sea level would generate only 700 horsepower at 10,000 feet, 490 horsepower at 20,000 feet, and 340 horsepower at 30,000 feet. This power degradation meant that aircraft performance, speed, climb rate, maneuverability deteriorated dramatically with altitude. The solution seemed obvious: compress the intake air before it entered the engine, artificially increasing its density and oxygen content. This would allow engines to maintain sea-level power output regardless of altitude. Two approaches emerged. The mechanically driven supercharger used gears connected to the engine's crankshaft to spin a compressor that pressurized intake air. This was relatively simple and reliable, but it consumed engine power to drive the compressor. The faster the compressor spun to maintain pressure at higher altitudes, the more power it consumed, creating diminishing returns. The alternative was the turbocharger, technically called a turbo supercharger, which used a turbine wheel spun by exhaust gases to drive the compressor. The exhaust gases, which would otherwise be wasted, provided the energy to compress intake air. In theory, this was vastly more efficient than mechanical supercharging because it recovered waste energy. In practice, it was extraordinarily complex and difficult to implement reliably. The engineering challenges were formidable. Exhaust gases exiting a piston engine reached temperatures of 1,400 to 1,600 degrees Fahrenheit. Materials had to withstand these temperatures while spinning at 15,000 to 25,000 RPM. The turbine wheel and compressor had to maintain precise balance at these speeds, or vibrations would destroy bearings within minutes. Oil lubrication systems had to function at the temperature extremes of red-hot turbines and sub-zero ambient temperatures at altitude. Control systems had to regulate boost pressure automatically because manual control was too complex for pilots managing other duties. Dr. Sanford Moss, working at General Electric's facility in Lynn, Massachusetts, pioneered American turbocharger development starting in 1918. Moss understood the theoretical advantages, but faced decade-long struggles making the technology reliable enough for practical use. Early turbochargers seized due to lubrication failures. Turbine wheels disintegrated from thermal stress. Control systems failed, causing engine damage from overboosting. By 1925, Moss had developed turbochargers that worked in laboratory conditions, but making them reliable enough for military service required another decade of refinement. European nations explored turbocharging during the 1920s and early 1930s, but reached different conclusions about its viability. French aviation engineers experimented with turbochargers on racing aircraft, achieving altitude records but experiencing frequent mechanical failures. British aircraft designers favored two-stage mechanical superchargers, accepting the power consumption penalty in exchange for mechanical simplicity and reliability. German engineers at Daimler-Benz and Junkers studied turbocharging extensively, but concluded the technology was impractical for combat aircraft. The German assessment, documented in Luftwaffe technical reports from the mid-1930s, reflected careful analysis and reasonable engineering judgment. German test pilots had experienced turbocharger failures firsthand during experimental programs. Turbines had disintegrated in flight, sending shrapnel through engine cowlings and sometimes through cockpits. Oil systems had failed at altitude, causing turbos to seize and engines to lose power instantly. Control systems had malfunctioned, overboosting engines and causing catastrophic mechanical failures. Temperature management had proven difficult, with exhaust manifolds glowing red hot and sometimes cracking from thermal stress. The German conclusion was that turbochargers required too much maintenance, failed too frequently, and were too heavy for the performance benefits they provided. German aircraft design philosophy emphasized reliability and maintainability. Combat aircraft had to be serviceable by mechanics with basic tools in field conditions. Turbochargers, with their complex oil systems, precise clearances, and exotic metallurgy, violated these principles. The Luftwaffe chose two-stage mechanical superchargers for its high-altitude fighters and bombers, accepting performance limitations in exchange for reliability. This decision made perfect sense given German operational requirements in 1935. The Luftwaffe was designed primarily for close air support of ground forces and battlefield interdiction. These missions occurred at low to medium altitudes, where turbochargers provided minimal advantages. The additional complexity, weight, and maintenance burden seemed unjustified. High-altitude strategic bombing wasn't part of German doctrine. Why optimize aircraft for flight regimes where they wouldn't operate? American aviation followed a different path, driven by different strategic requirements. The Air Corps Tactical School at Maxwell Field, Alabama, developed doctrine during the 1930s, emphasizing strategic bombing of industrial targets deep in enemy territory. This doctrine assumed bombers would face fighter opposition and anti-aircraft fire. Operating at maximum altitude provided advantages against both threats. Fighters struggled to intercept at high altitude due to performance degradation. Anti-aircraft fire became less accurate as altitude increased due to longer time of flight and greater susceptibility to wind drift. The requirement for high-altitude operations made turbocharging essential despite its complexity. The Army Air Corps funded continued development work at General Electric, and by 1938, Moss and his team had developed the Type B turbocharger that was reliable enough for production aircraft. The breakthrough came from better materials, improved oil systems, and automatic control mechanisms that managed boost pressure without pilot intervention. Boeing incorporated turbochargers into the Model 299, the prototype that became the B-17 Flying Fortress. Each of the four Wright R-1820 Cyclone radial engines was equipped with a General Electric B-Series turbocharger mounted in the rear fuselage. Exhaust from each engine was ducted through pipes to the turbo, where the hot gases spun the turbine wheel. The turbine drove the compressor on the opposite end of the common shaft. The compressor drew in ambient air, compressed it to sea level density or higher, cooled it through an intercooler, and delivered it to the engine's carburetor. The system was extraordinarily complex by 1930s standards. Each turbocharger installation included the turbo unit itself, exhaust ducting from engine to turbo, intake ducting from turbo to engine, an oil supply system with pressure and scavenge pumps, an intercooler to cool compressed air, waste gates to control boost pressure, automatic regulators to manage waste gate position, instrumentation for monitoring turbine speed and manifold pressure, and electrical systems to power the controls. The entire installation added approximately 400 pounds per engine, 1,600 pounds total for all four turbos. German intelligence first observed turbocharged B-17s during visits to American aircraft factories in 1938 as part of technology exchange programs. The Luftwaffe attaché in Washington filed detailed reports describing the turbocharger installations. The analysis was skeptical. The German engineers noted the complexity, the number of components that could fail, the maintenance requirements, and the weight penalty. One report from early 1939 stated that American designers had accepted unjustifiable complexity in pursuit of high-altitude performance that wouldn't prove valuable in actual combat operations. This assessment reflected German operational experience, where combat occurred at 12,000 to 18,000 feet, altitudes where mechanical superchargers worked adequately. The Germans assumed American bombers would operate similarly. The idea that bombers might routinely fly at 25,000 to 30,000 feet seemed impractical. At those altitudes, crew members required oxygen systems that were bulky and prone to failure. Temperatures reached -40 to -60 degrees Fahrenheit, requiring electrically heated suits. Engines consumed more fuel at altitude due to decreased efficiency. Formation flying became more difficult due to thinner air and slower airspeeds. The Germans weren't wrong about these challenges. They were real and significant. What German analysis missed was that American engineering culture would solve each problem systematically, rather than abandoning high-altitude operations as too difficult. The oxygen systems were improved through testing and refinement. Heated suits were developed and made reliable. Fuel consumption was accepted as a cost worth paying for the tactical advantages altitude provided. Formation flying techniques were developed specifically for high-altitude operations. When war began in Europe in September 1939, the Luftwaffe's performance against Polish, French, and British forces seemed to validate German design choices. Bf-109 fighters with mechanical superchargers dominated opponents at combat altitudes. bombers operating at medium altitudes proved effective against ground targets. The complex American bombers with their troublesome turbochargers seemed like solutions to problems that didn't exist. The Battle of Britain in summer 1940 reinforced German confidence. Luftwaffe bombers attacked England flying at 15,000 to 20,000 feet, altitudes where RAF fighters could intercept effectively. The idea of flying higher to avoid interception wasn't considered viable because German bombers lacked the performance to operate efficiently at 25,000 feet or above. The She-111 and Do-17 bombers used mechanical superchargers that provided adequate power at medium altitude but couldn't sustain operations above 22,000 feet. American observers watching the Battle of Britain drew different conclusions. The heavy losses suffered by unescorted German bombers suggested that altitude advantages would be crucial for daylight strategic bombing. Flying above the effective ceiling of enemy fighters would reduce interception opportunities. Flying above the effective range of heavy anti-aircraft artillery would reduce losses to flak. The B-17s Turbochargers, which German engineers had dismissed as overcomplicated, suddenly seemed like critical strategic advantages. Production B-17s entering service with the Army Air Forces in 1941 demonstrated performance that matched predictions. The B-17E model, entering service in late 1941, could cruise at 27,000 feet with full bomb load. Maximum altitude exceeded 35,000 feet when lightly loaded. This was not theoretical ceiling, where the aircraft barely maintained flight, but operational altitude, where the bomber could maintain formation, maneuver reasonably, and defend itself effectively. The key difference was power available at altitude. A B-17E at 27,000 feet, with turbochargers maintaining sea-level manifold pressure, had engines producing nearly full-rated horsepower. The Wright R-1820 Cyclones generated 1,200 horsepower each at military power settings. With turbocharging maintaining intake air density, this power output was available at altitude. Without turbochargers, those same engines at 27,000 feet would produce perhaps 500 horsepower each, insufficient to sustain flight with combat loads. German fighters attempting to intercept B-17s at these altitudes faced crippling performance degradation. The Bf-109F, the frontline Luftwaffe fighter in 1941, used a single-stage, mechanically driven supercharger. At 27,000 feet, its Daimler-Benz DB601 engine produced approximately 40% of its sea-level power output. Maximum speed at altitude dropped to approximately 340 Messerschmitt, compared to 390 at optimal altitude of 18,000 feet. Rate of climb degraded to less than 500 feet per minute. Maneuverability suffered, as thinner air required higher airspeeds to maintain lift, and the engines couldn't generate power for rapid acceleration. The mathematical relationship between altitude and interception capability was brutal and unforgiving. A Bf-109F at sea level could climb to 20,000 feet in approximately 9 minutes. The same aircraft climbing to 30,000 feet required 18 to 20 minutes because the climb rate decreased exponentially as power output declined. This meant that intercepting bombers at 30,000 feet required German fighters to begin climbing long before the bombers arrived, consuming fuel and limiting combat duration. The operational implications became clear when the 8th Air Force began bombing missions from England in August 1942. Early missions targeted occupied France and the Low Countries, flying at 23,000 to 25,000 feet. German fighters intercepted, but struggled to press attacks effectively at these altitudes. Luftwaffe pilots reported that their aircraft handled sluggishly, that acceleration was poor, that maintaining position during attacks required careful energy management, and that the Americans seemed comfortable at altitudes where German fighters were gasping. By late 1942, American mission planners were deliberately exploiting altitude advantages. Missions to targets in Germany flew at $27,000 to 29,000 feet, pushing German fighters to their performance limits. The B-17F models entering service had improved turbochargers with better oil systems and more reliable controls. These aircraft cruised comfortably at altitudes where the Bf-109F struggled to reach at all. The Luftwaffe response was predictable: develop fighters with better high-altitude performance. The Bf-109G, introduced in late 1942, featured the DB605 engine with improved supercharging. But this was still a single-stage mechanical supercharger with the same fundamental limitations. The 109G could reach 30,000 feet, but performance at that altitude was marginal. Speed dropped to 320 mph. Climb rate was anemic. Maneuverability was severely compromised. The FW-190A, entering service in significant numbers in 1943, actually performed worse at high altitude than the 109G. The BMW 801 radial engine with its mechanical supercharger was optimized for low to medium altitude performance. Above 25,000 feet, the 190A's performance degraded rapidly. Maximum speed at 30,000 feet was barely 300 mph. The aircraft was nearly useless for intercepting high-flying B-17s. German engineers recognized the altitude problem and developed solutions, but implementation was slow and production was limited. The Bf-109H was designed specifically for high-altitude interception with enlarged wings and improved supercharging, but it never entered production. The TA-152H incorporated a three-stage supercharging system that gave excellent high-altitude performance, but only a handful were built before war's end. The GM-1 nitrous oxide boost system could temporarily increase power at altitude, but it was complex, dangerous, and available only to specialist units. The fundamental problem was that Germany had chosen a different technological path in the 1930s, and changing that path in wartime proved extraordinarily difficult. Developing new engines with better supercharging required years. Retrofitting existing fighters with turbochargers wasn't practical, given the complexity and weight of the installations. The Luftwaffe was trapped by earlier design decisions that had seemed reasonable, but left their fighters incapable of effectively engaging bombers at altitudes where the Americans operated routinely. American bomber crews in 1943 understood they possessed an advantage that German fighters couldn't counter effectively. Briefings before missions emphasized maintaining altitude discipline. Pilots were instructed to climb to assigned altitudes early and maintain those altitudes throughout the mission, even if it meant burning extra fuel. The altitude advantage was survival. Every 1,000 feet above the German fighters' effective ceiling was another measure of safety. The physical challenges of high-altitude operations were severe but manageable with proper equipment and procedures. At 30,000 feet, atmospheric pressure was approximately 30% of sea level. Crew members required supplemental oxygen delivered through masks connected to liquid oxygen systems. Temperatures at altitude ranged from -40 to -60 degrees Fahrenheit. Crew members wore electrically heated suits, though these frequently malfunctioned, causing frostbite injuries that were among the most common non-combat casualties. The human factors at extreme altitude were significant. Hypoxia from oxygen system failures or mask problems occurred frequently. Symptoms included confusion, euphoria, poor judgment, and eventual unconsciousness. Crew members had to monitor each other constantly, watching for signs that someone's oxygen wasn't functioning properly. Frostbite from equipment failures or exposure to slipstream through open gun positions caused permanent damage. Some gunners lost fingers or toes to frostbite during long missions. But these challenges were accepted because the altitude advantage was worth the discomfort and risk. German fighters that could barely reach the bomber's altitude couldn't press sustained attacks. Their performance at extreme altitude was so degraded that even damaged B-17s could often escape by maintaining altitude where German fighters couldn't follow effectively. Luftwaffe pilots learned through bitter experience that attacking bombers at 30,000 feet meant their aircraft were operating at the edge of flight envelopes, where any battle damage or pilot error could result in stalls, spins, or loss of control. The turbocharger systems that enabled this altitude capability required constant maintenance and attention. Each turbo represented a complex mechanical system with hundreds of parts operating under extreme conditions. Turbine wheels spun at 20,000 RPM, experiencing centrifugal forces that stressed materials to their limits. Bearings operated in environments where temperatures varied from 1,400 degrees on the turbine side to sub-zero on the compressor side across a shaft distance of less than 6 inches. Oil systems were critical and troublesome. The turbos required high-pressure oil flow for bearing lubrication and cooling. Oil was supplied from the engine's lubrication system through pressure lines, then scavenged back through return lines. If oil pressure dropped, bearings would fail within seconds. If scavenge pumps couldn't return oil quickly enough, the turbo would flood and seize. Temperature management was critical because oil could coke from heat on the turbine side or become too viscous from cold on the compressor side. Ground crews learned turbocharger maintenance through extensive training and hard experience. Pre-flight inspections checked oil levels, examined ducting for leaks, verified wastegate operation, tested automatic regulators, and looked for cracks in exhaust manifolds or turbine housings. Post-flight inspections examined turbine wheels for damage, checked bearing condition through oil analysis, measured shaft play to detect wear, and inspected intercoolers for leaks or damage. Turbocharger failures during missions were relatively common despite maintenance efforts. Oil system failures were most frequent. A loss of oil pressure would cause the turbo to seize, losing boost for that engine. The engine would continue running, but power output would drop dramatically as ambient air pressure at altitude couldn't sustain combustion. Aircraft could usually return on 3 engines, though maintaining formation altitude became difficult. More serious failures occurred when turbine wheels disintegrated. The wheels spun at tremendous speeds, and any imbalance from thermal stress, foreign object damage, or manufacturing defects could cause catastrophic failure. When a turbine wheel disintegrated, fragments traveled outward at velocities exceeding 1,000 feet per second. The turbo housing usually contained the debris, but sometimes fragments penetrated and damaged surrounding structure, control cables, or adjacent systems. Despite these reliability challenges, the turbocharger systems proved remarkably effective given their complexity. Approximately 70% to 80% of B-17s completing missions had all 4 turbos functioning normally throughout the flight. Another 15% to 20% experienced turbo problems but completed missions with degraded performance. Only 5% to 10% of turbo failures were serious enough to force mission abort or cause aircraft loss. This reliability was achieved through continuous engineering improvements, rigorous maintenance, and extensive crew training. The production statistics reveal the scale of America's commitment to turbocharged strategic bombing. Boeing, Douglas, and Vega produced 12,631 B-17s during the war. Each aircraft had 4 turbochargers, totaling 50,924 units produced. General Electric's turbocharger production lines operated continuously, refining designs and improving reliability throughout the war. The E-Series turbochargers on early B-17Fs gave way to improved B-Series and C-Series turbos on later models, each iteration improving reliability and reducing maintenance requirements. The engineering refinement was continuous. Early turbochargers required overhaul after approximately 200 hours of operation. Later models extended this to 400 to 500 hours. Automatic control systems improved, reducing pilot workload and preventing overboost conditions that could damage engines. Intercooler designs evolved to provide better cooling with less weight and drag. Oil system improvements reduced failure rates. Materials development provided alloys that better withstood the thermal and mechanical stresses. The industrial capacity to produce tens of thousands of complex turbocharger systems while simultaneously improving their design demonstrated American engineering and manufacturing capabilities that Germany couldn't match. German industry struggled to produce sufficient conventional mechanical superchargers for its fighters. developing and producing turbochargers on American scales was simply impossible, given resource constraints and manufacturing capacity limitations. The operational impact of altitude advantages became undeniable by mid-1943. 8th Air Force mission reports consistently noted that German fighter opposition was less effective at altitudes above 28,000 feet. Luftwaffe pilots would attempt intercepts but struggled to maintain formation, press attacks, or inflict significant damage. The Americans weren't invulnerable. Determined German pilots could and did shoot down high-flying B-17s, but the altitude advantage made interception exponentially more difficult. The mission to Schweinfurt on October 14, 1943, demonstrated both the power and limitations of altitude advantage. The 291 B-17s dispatched flew at altitudes ranging from 26,000 to 32,000 feet, depending on group and weather conditions. German fighters attempted massive coordinated attacks, but struggled with the altitude. Luftwaffe commanders assembled approximately 300 fighters, but many couldn't maintain effective combat altitude for sustained periods. Pilots reported climbing to 28,000 or 29,000 feet, making a single attack pass, then having to descend to rebuild speed and prepare for another attempt. The Americans lost 60 bombers on the mission, a devastating 20% loss rate that temporarily suspended deep penetration missions. But German fighter losses were equally severe at 35 to 40 aircraft destroyed. More significantly, German pilots reported expending enormous fuel reserves climbing to intercept altitude, limiting combat time over the target. Many fighters ran so low on fuel during extended high-altitude intercepts that they couldn't pursue damaged bombers that fell behind formations. The altitude advantage, while not preventing losses, made those losses more expensive for German defenders. Every bomber shot down cost German fighters more fuel, more time, more risk at altitudes where engine failures or battle damage could prove fatal. The exchange ratios gradually shifted in favor of the bombers as altitude tactics combined with improved fighter escort and combat box formations. German technical intelligence by late 1943 finally acknowledged that turbocharging gave American bombers decisive altitude advantages. Captured documents show Luftwaffe engineering staff recommending crash programs to develop high-altitude fighters. But implementing these recommendations proved impossible. Germany's industrial capacity was stretched beyond limits. Aircraft factories were being bombed regularly. Engine development facilities faced material shortages. The fuel crisis meant that even if high-altitude fighters were developed, there wouldn't be sufficient aviation gasoline to operate them. The DB605 engine with improved supercharging entered production for the Bf-109 G6, providing modestly better high-altitude performance. The FW-190D with the Jumo 213 inline engine gave better altitude capability than the radial-powered A model, but these were incremental improvements that narrowed the gap slightly without eliminating American advantages. B-17s still operated at altitudes where German fighters struggled. The introduction of the B-17G model in late 1943 with the chin turret improved defensive firepower, but the altitude capability remained the critical advantage. Mission planners routinely assigned bombing altitudes of 28,000 to 30,000 feet. Knowing this pushed German interceptors to performance limits. Weather permitting, groups would climb even higher, with some missions flown at 32,000 to 33,000 feet, where German fighters could barely reach. The psychological impact on German fighter pilots was significant and cumulative. Pilots accustomed to altitude advantages over Soviet aircraft on the Eastern Front found themselves at severe disadvantages against American bombers. The physical strain of operations at extreme altitude, hypoxia despite oxygen masks, extreme cold despite heated suits, fatigue from fighting against sluggish controls, accumulated over missions. Some pilots requested transfers away from bomber interception duties, preferring the lower altitude combat against Allied fighters to the misery of high altitude intercepts against formations they couldn't effectively engage. The human cost of high altitude operations affected both sides but differently. American bomber crews faced the physical challenges of operating at extreme altitude, but had equipment that mostly worked and training that prepared them reasonably well. Frostbite, hypoxia, and cold injuries were common but manageable. German fighter pilots faced similar physical challenges, but with equipment less optimized for sustained high-altitude operations. Oxygen systems in German fighters were adequate, but not generous. Cockpit heating was minimal. The physical toll of repeatedly climbing to extreme altitude, attempting combat, then repeating the cycle multiple times per mission exhausted pilots in ways that low-altitude combat didn't. The strategic implications extended beyond individual missions. The ability to operate at altitudes where interception was difficult allowed American bombers to reach any target in Germany with reasonable confidence of penetrating defenses. Deep strikes to Berlin, Munich, and distant industrial centers became routine. The altitude advantage didn't prevent losses, but it made sustained strategic bombing feasible where it might otherwise have been prohibitively expensive. The introduction of P-51 Mustang escorts in early 1944 combined with altitude advantages to create conditions where German fighter losses became unsustainable. Luftwaffe fighters climbing to intercept altitude found themselves vulnerable to escorts that could operate effectively at those altitudes, with drop tanks providing extended range. German fighters that did reach bomber altitude were often bounced by escorts diving from above. The combination proved devastating. By spring 1944, German fighter pilot losses exceeded replacement rates. The veterans who had learned high-altitude combat techniques were being systematically eliminated. Their replacements, rushed through abbreviated training programs with minimal flight hours, lacked the skills for effective high-altitude interception. Fuel shortages limited training further. By D-Day in June 1944, the Luftwaffe fighter force was a shell of its former capability, unable to effectively contest Allied air superiority, even at medium altitudes, much less at the extreme altitudes where B-17s operated. The technological assessment of turbocharging post-war recognized it as a decisive advantage that German engineering choices in the 1930s had foreclosed. German aircraft designers had made reasonable decisions based on their operational requirements and engineering philosophy, but those decisions created path dependencies that couldn't be reversed in wartime. American designers had accepted complexity and maintenance burdens in pursuit of high-altitude performance, and that gamble paid enormous dividends when doctrine required strategic bombing at extreme altitudes. The B-17's service ceiling with full combat load exceeded 35,000 feet, though missions rarely flew above 32,000 feet due to crew endurance limits and bombing accuracy considerations. This ceiling was approximately 7,000 feet higher than the effective combat ceiling of German fighters. That 7,000 feet represented a buffer zone where American bombers operated with relative impunity, where German fighters struggled to reach even under ideal conditions, where interception required so much fuel that combat time was measured in minutes rather than the hours available at medium altitudes. The physics were unforgiving and absolute. Air density at 30,000 feet is 30% of sea level. Engines without boost systems produce 30% of sea level power. Aircraft flying at 30% power cannot maintain speed, cannot climb, cannot maneuver effectively. Turbochargers restored sea level density artificially, allowing engines to produce full power regardless of altitude. German fighters with mechanical superchargers could compensate partially, but not completely. They operated at the edge of performance envelopes, while Americans cruised comfortably below their capabilities. The maintenance burden that German engineers had cited as reason to avoid turbocharging proved manageable for American forces with their different logistics philosophy. American doctrine emphasized depot-level maintenance with extensive spare parts stocks. Aircraft rotated through maintenance cycles regularly. Component failures were addressed by replacement rather than repair in forward areas. This approach required massive logistics infrastructure, but it worked. German doctrine emphasized field maintenance and repair, minimizing logistics burden but limiting capability to support complex systems. The fuel consumption penalty that turbocharging imposed was significant but acceptable. Turbocharged engines consumed approximately 15% more fuel than mechanically supercharged engines at the same power output due to intake system losses and heat rejection requirements. But this penalty was worth paying for the altitude capability it provided. American bomber radius with maximum fuel load exceeded 1,500 miles, sufficient to reach any target in Germany from English bases. The fuel consumption penalty reduced this radius modestly, but not enough to affect target selection. The weight penalty of approximately 1,600 pounds for 4 complete turbocharger installations affected performance margins but not mission capability. B-17s could carry bomb loads of 4,000 to 8,000 pounds, depending on target distance, adequate for strategic bombing requirements. The turbocharger weight came from fuel capacity and bomb load margins, not from mission-critical capability. The trade-off was clearly worthwhile. The engineering sophistication of the turbocharger systems represented American technical capabilities that German intelligence had underestimated. The automatic control systems that managed boost pressure involved hydraulic actuators, pressure sensors, mechanical computers that integrated multiple inputs, and fail-safe mechanisms that prevented overboost conditions. These systems functioned reliably in combat conditions with minimal pilot intervention, allowing aircrew to focus on navigation, bombing, and defensive operations rather than constant engine management. The intercooler systems that cooled compressed air before it entered the engines demonstrated practical thermodynamic engineering. Compressing air increased its temperature significantly. Compressed air could reach 300 to 400 degrees Fahrenheit. Feeding this hot air directly to engines would reduce power output and risk detonation. The intercoolers used ram air flowing through radiator-like cores to cool compressed air to manageable temperatures. This required careful design to balance cooling effectiveness against drag penalties from the intercooler installation. The exhaust systems that ducted hot gases from engine to turbo, then overboard, represented challenging materials engineering. Exhaust manifolds operated at 1,400 to 1,600 degrees Fahrenheit continuously during operations. Stainless steel alloys had to maintain strength at these temperatures while resisting oxidation and thermal fatigue. Expansion joints had to accommodate thermal growth without cracking. Gasket materials had to seal reliably at temperature extremes. The durability of these systems under combat conditions demonstrated manufacturing quality that German industry couldn't consistently match by mid-war. The strategic vindication of turbocharging came through mission statistics that showed altitude capability directly correlating with survival rates. Groups flying missions at 28,000 feet or above had loss rates approximately 30% lower than groups at 25,000 feet, and 50% lower than hypothetical missions at 20,000 feet where German fighters operated most effectively. This survival advantage accumulated over campaign duration. Every mission where altitude provided protection was a mission where more crews survived, more aircraft returned, and more industrial targets were destroyed. The cumulative effect was that by late 1944, American bombers operated essentially unmolested over Germany. Luftwaffe fighter strength had been destroyed through attrition that altitude advantages had accelerated. German pilots who survived early missions faced increasingly impossible odds. The combination of altitude capability, fighter escort, and formation defensive firepower created conditions where bomber interception became a mission with survival probability approaching zero for Luftwaffe pilots. The final missions of the European War, saw B-17s bombing at medium altitudes, not because high altitude was impossible, but because German fighter opposition had ceased. The altitude capability remained available but unnecessary when there were no defenders to avoid. This complete reversal from 1943, when every 1,000 feet of altitude provided critical survival advantages, demonstrated how thoroughly the combination of American technology and strategic persistence had destroyed German defensive capability. The human story behind turbocharging involves thousands of engineers, production workers, maintenance crew members, and air crew who made the technology work under operational conditions. Sanford Moss and his team at General Electric spent 2 decades refining turbocharger technology from laboratory curiosity to combat-reliable systems. Their persistence through countless failures, design iterations, and technical setbacks created the foundation for strategic bombing success. The production workers at GE's facilities manufactured tens of thousands of precision turbo machinery units under wartime pressure. The tolerances required for turbine wheels, compressor impellers, and bearing assemblies demanded skilled machining and inspection. Quality control was critical because failures could destroy aircraft and kill crews. The workers understood that every turbocharger they built would face combat conditions, and their craftsmanship directly affected aircrew survival. The maintenance personnel who serviced turbocharger systems in English weather demonstrated dedication that enabled operational success. Working in cold, rain, darkness, they performed complex maintenance procedures on schedule-driven timetables. Aircraft had to be ready for missions regardless of conditions. Turbo problems discovered during pre-flight inspections required rapid troubleshooting and repair. Maintenance crews developed expertise through experience, learning to diagnose problems quickly and implement repairs efficiently. The aircrew who flew turbocharged B-17s understood that altitude capability directly affected their survival odds. Pilots managed turbocharger systems through mission duration, monitoring manifold pressure, turbine speed, and oil pressure while simultaneously flying formation, navigating and coordinating with crew members. They learned to recognize system malfunctions early, unusual sounds, vibrations, instrument fluctuations, and respond appropriately before minor problems became catastrophic failures. Flight engineers became turbocharger specialists out of necessity. Their station in the top turret section of the B-17 positioned them near the turbo control panel, with instruments monitoring all 4 systems. They watched the gauges constantly, noting trends that indicated developing problems. A gradual increase in turbine speed suggested wastegate issues. Fluctuating oil pressure indicated bearing wear or oil system problems. Temperature variations warned of exhaust leaks or intercooler damage. The training pipeline for B-17 crews included extensive instruction on turbocharger operation and emergency procedures. Student pilots learned the systems during transition training, understanding not just how to operate them, but why they functioned as they did. The thermodynamic principles, the mechanical relationships, the failure modes, all were taught in sufficient detail that pilots could troubleshoot problems and make informed decisions when systems malfunctioned in combat. Flight engineers received even more detailed training. They learned to field repair certain turbo problems, replacing oil lines, adjusting wastegates, bypassing damaged components. They understood that maintaining altitude capability might mean accepting degraded performance from damaged turbos rather than shutting them down completely. A turbo with marginal oil pressure might continue functioning long enough to complete the mission if carefully managed, even if it required replacement afterward. The operational doctrine that evolved around turbocharger capabilities reflected understanding that altitude was both an advantage and a commitment. Once formations climbed to 30,000 feet, descending meant losing the advantage that made the mission feasible. Groups maintained altitude even when individual aircraft suffered turbo failures and struggled to keep position. The formation discipline that characterized American bomber operations was partly enabled by and partly dependent on turbocharger reliability. Aircraft with multiple turbo failures would fall behind and descend, becoming vulnerable. But single turbo losses could often be managed, allowing aircraft to maintain formation long enough to reach the relative safety of friendly territory. The fuel management implications of high-altitude operations required careful planning and execution. Climbing to 30,000 feet consumed significantly more fuel than cruising at that altitude. Mission planners calculated fuel requirements precisely, accounting for the climb, cruise, combat operations, and return. The turbochargers enabled high-altitude cruise efficiency that partially offset the climb fuel consumption. At 30,000 feet, the B-17's engines operated at high power settings to overcome the reduced aerodynamic efficiency of thin air, but turbochargers maintained combustion efficiency that mechanical superchargers couldn't match. The maximum range of approximately 2,000 miles with normal fuel load and 3,000 miles with auxiliary tanks enabled missions to any target in Germany from English bases. The fuel reserves required for formation assembly, climb to altitude, navigation uncertainties, weather diversions, and combat contingencies were substantial. But the mission planning had matured to the point where fuel exhaustion was rarely a factor in mission outcomes. The combination of reliable range calculations and dependable engine performance gave crews confidence that fuel would be available when needed. The weather considerations at extreme altitude were significant and sometimes mission limiting. Contrail formation at high altitude created visibility issues that complicated both defensive coordination and bombing accuracy. The condensation trails streaming from engines marked bomber positions visibly from great distances. German fighters used contrails to locate formations and plan interception routes. Mission planners factored contrail formation into operational decisions, sometimes accepting the visibility penalty for the altitude advantages. Temperature inversions and atmospheric conditions at altitude sometimes created situations where contrails formed at certain altitudes, but not others. Formations would climb or descend slightly to find altitude bands where contrails minimized. This tactical use of atmospheric conditions demonstrated the operational sophistication that American bomber crews developed through experience. They understood the environment at 30,000 feet intimately, the temperature gradients, humidity variations, wind patterns, and used that knowledge to optimize mission effectiveness. The structural considerations of sustained high-altitude flight proved less problematic than German engineers had predicted. The B-17 airframe handled the pressure differential between cabin altitude and outside atmospheric pressure without significant issues. While the aircraft wasn't pressurized in the modern sense, the fuselage was sealed sufficiently that cabin altitude with oxygen supplementation remained manageable. The temperature differential between exterior skin exposed to minus 50-degree air and interior spaces warmed by equipment and crew didn't create structural problems. The engineering margins built into the B-17 design proved adequate for the stresses of high-altitude combat operations. The wing structure withstood ice accumulation that could add thousands of pounds during climbs through weather. The control surfaces maintained authority at the high true airspeeds characteristic of altitude operations. The landing gear operated reliably despite thermal cycling between extreme cold at altitude and relatively warm temperatures at ground level. The aircraft was overbuilt by some standards, but that structural conservatism contributed to survivability and reliability. The defensive gunnery challenges at high altitude required adaptation and training. The ball turret gunner at 30,000 feet operated in an environment where temperatures inside his plexiglass sphere reached minus 40 degrees despite electrical heating. The plexiglass sometimes fogged or frosted, reducing visibility. The oxygen mask connection points were vulnerable to disconnection during aircraft maneuvering. Yet ball turret gunners continued to function, engaging fighters that attacked from below, maintaining their defensive sector despite conditions that tested human endurance limits. Waist gunners facing open windows at 30,000 feet dealt with slipstream velocities and temperatures that made extended exposure dangerous. The oxygen requirements, heating suit dependencies, and communication difficulties created conditions where maintaining effective defense required extraordinary determination. Frostbite from touching exposed metal with bare skin occurred instantly. Equipment failures that required manual intervention without gloves meant accepting injury to restore functionality. Tail gunners, isolated in the aircraft's rear section, faced similar challenges with the added psychological burden of facing attacking fighters alone. The tail position was the most dangerous statistically, taking the highest percentage of casualties among crew positions. Yet tail gunners maintained their posts, operating their guns through attacks that killed or wounded them, providing defensive fire that was often the only thing between the aircraft and destruction. The bombing accuracy from 30,000 feet proved adequate for strategic targets despite the altitude challenges. The Norden bomb sight, a sophisticated analog computer that calculated release points based on altitude, airspeed, wind drift, and target motion, functioned effectively at extreme altitude when properly calibrated. Bombardiers trained extensively in high-altitude bombing procedures, understanding the longer bomb fall times and greater susceptibility to wind drift that altitude created. The typical bombing pattern from 30,000 feet with a 1,000-pound general-purpose bomb resulted in impact approximately 30 seconds after release. During that fall time, crosswinds could drift the bomb hundreds of feet laterally. The bombardier had to calculate this drift and offset the aim point accordingly. The Norden sight performed these calculations when provided accurate wind data, but obtaining accurate wind information at altitude required careful observation and sometimes trial and error corrections. The circular error, probable, CP, the radius within which 50% of bombs fell, from 30,000 feet was approximately 1,200 to 1,500 feet under good conditions. This accuracy was adequate for large industrial targets like factories, rail yards, and refineries. It was inadequate for precision targets like bridges or specific buildings, but the strategic bombing doctrine accepted this limitation, targeting industrial complexes rather than individual structures. The German response to American high-altitude bombing evolved throughout 1943 and 1944 as the Luftwaffe adapted what tactics it could with available equipment. Unable to develop fighters that could operate effectively at 30,000 feet in time to matter, German commanders emphasized alternative approaches. Standing off and firing rockets from beyond defensive gun range became more common. The Werfer Granit 21 rocket could be launched from 1,000 to 1,200 yards, outside the effective range of defensive guns, though accuracy was poor and actual kills were rare. The heavily armed and armored FW-190 variants, designated as bomber destroyers, accepted performance penalties in exchange for survivability and firepower. These aircraft carried 30mm and even 50mm cannon that could destroy bombers with single hits, but the additional weight and drag made them slow and unmaneuverable, vulnerable to escort fighters. The few successful attacks by these heavily armed fighters occurred when escorts weren't present or were distracted. With the introduction of ubiquitous P-51 escort in 1944, the slow bomber destroyers became easy kills. The German development of the Me-163 rocket-powered interceptor and Me-262 jet fighter represented attempts to overcome the altitude and speed disadvantages through revolutionary technology. The Me-163 could reach 30,000 feet in under 3 minutes and had a top speed exceeding 550 mph, but its fuel endurance was measured in minutes, and its operational record was poor. The Me-262 had performance advantages over piston engine fighters, but arrived too late and in too few numbers to affect the strategic balance. Both aircraft represented German recognition that conventional piston fighters couldn't effectively counter high-altitude American bombers. The statistical evidence of turbocharger effectiveness appears in loss rate data correlated with operational altitude. 8th Air Force missions flown at 28,000 feet or above during 1943 had average loss rates of 4.2% compared to 6.1% for missions at 24,000 to 27,000 feet and 8.3% for missions below 24,000 feet. This correlation held even accounting for target difficulty, route exposure, and escort availability. The altitude advantage provided by turbochargers directly translated to improved survival rates that accumulated across hundreds of missions. The cumulative effect over the campaign was that approximately 2,000 to 3,000 additional bombers survived missions due to altitude advantages that wouldn't have survived at lower altitudes. With 10 crew members per bomber, this represented 20,000 to 30,000 aircrew who completed tours and went home because turbochargers allowed operations at altitudes where German interceptors struggled. These numbers are estimates based on statistical modeling, but they represent real human lives saved by engineering decisions made a decade before the war. The industrial production comparison between American turbocharger manufacturing and German supercharger production reveals the magnitude of American advantages. General Electric produced over 50,000 turbochargers for B-17s alone, plus thousands more for other aircraft types. Each turbocharger represented precision manufacturing with tolerances measured in thousandths of an inch, exotic materials like heat-resistant steel alloys, and quality control ensuring reliable operation under extreme conditions. German industry produced mechanical superchargers in comparable numbers, but couldn't match the performance characteristics turbochargers provided at high altitude. The technological sophistication extended beyond the turbomachinery itself to the control systems, intercoolers, and integration with aircraft systems. The automatic wastegate controls that regulated boost pressure represented mechanical computing before electronic computers existed. These systems sensed manifold pressure, compared it to preset values, and adjusted wastegate position to maintain desired boost. They did this continuously and automatically, responding to altitude changes, throttle movements, and atmospheric variations without pilot intervention. The intercooler technology that cooled compressed air represented practical heat exchanger design, optimized for the specific requirements of turbocharger applications. The cores were designed to maximize heat transfer while minimizing pressure drop and drag. The materials resisted corrosion from condensation and contamination from oil vapor in the compressed air. The installations were positioned to utilize ram air effectively while protecting the cores from battle damage. The oil system engineering solved the challenge of lubricating bearings operating across extreme temperature gradients. Oil entered the turbocharger at approximately 180 degrees Fahrenheit from the engine lubrication system. On the turbine side, it faced radiant heat from components at 1,400 degrees. On the compressor side, it faced temperatures well below freezing at altitude. The oil formulation, flow rates, and system design all had to account for these extremes while maintaining adequate lubrication under centrifugal forces from 20,000 RPM rotation. The maintenance documentation and training materials developed for turbocharger systems filled volumes and represented accumulated knowledge from years of operational experience. Technical orders specified inspection procedures, overhaul intervals, and troubleshooting guides. Maintenance crews studied these materials and applied the procedures during daily operations. The institutional knowledge about what failures looked like, how to diagnose problems, and how to repair or replace components efficiently was passed from experienced mechanics to new personnel through formal training and informal mentorship. The post-war analysis of turbocharger contribution to Allied victory recognized it as a decisive technology advantage that German engineering philosophy had foreclosed. The U.S. Strategic Bombing Survey concluded that the ability to operate at extreme altitude made strategic bombing feasible against defended targets. Without altitude advantages, loss rates would have forced either abandonment of daylight operations or acceptance of casualty rates that would have exhausted crew replacement pipelines. The British experience validated this conclusion. RAF Bomber Command, operating at night at medium altitudes, suffered loss rates that averaged 5% to 7% throughout the campaign. These rates were sustainable, but barely so, and they required continuous crew replacement at rates that strained training capacity. American daylight operations with altitude advantages achieved comparable or better loss rates while delivering bombs with significantly better accuracy. The combination of precision and survivability that turbocharging enabled justified the complexity and maintenance burden. The German perspective post-war, documented in interrogations of Luftwaffe commanders and technical personnel, consistently acknowledged that altitude capability was a critical American advantage they couldn't counter. General Adolf Galland, who commanded Luftwaffe fighter forces, stated in 1945 that the Americans' ability to operate at 30,000 feet with full combat capability made interception problematically expensive in fuel, time, and pilot fatigue. He noted that German fighters climbing to extreme altitude consumed so much fuel that combat time was minimal, and the physical toll on pilots attempting repeated high-altitude intercepts degraded effectiveness across missions. The engineering lessons learned from turbocharger operations influenced post-war aircraft development extensively. The principle that exhaust energy recovery could provide altitude performance became standard in piston engine design. The Korean War era B-29 and B-50 bombers used turbochargers derived from B-17 technology. The early jet engines incorporated turbine technology that evolved partly from turbocharger development. The understanding of high-altitude operations, pressure management, and temperature control gained from turbocharger experience informed jet engine development and high-altitude aircraft design for decades. The human achievement behind turbocharger technology deserves recognition beyond technical specifications and performance data. Sanford Moss spent his career pursuing a technology that many experts dismissed as impractical. His persistence through failures and setbacks, his methodical approach to solving problems, and his refusal to accept that complexity made the technology unviable, created the foundation for strategic bombing success. He never flew combat missions or faced enemy fire, but his contribution to victory was as significant as any combat commander. The GE engineering teams who refined Moss's concepts into production-ready systems demonstrated the depth of American technical capability. They solved problems in thermodynamics, materials science, mechanical engineering, and control systems that had no precedent. They designed for manufacture at scale, creating systems that could be produced in tens of thousands while maintaining quality and reliability. They supported fielded systems with continuous improvements, taking lessons from operational experience and implementing design changes that enhanced performance and reduced maintenance burden. The military leadership that committed to high-altitude strategic bombing, despite the technical challenges and operational uncertainties, made decisions that determined the course of the air war. The Army Air Corps in the 1930s could have followed the German path, accepting altitude limitations in exchange for mechanical simplicity. Instead, they committed to turbocharging, despite knowing it would create maintenance challenges and require extensive logistic support. That decision, made years before war began, created capabilities that proved strategically decisive. The crews who flew turbocharged bombers into combat demonstrated courage and professionalism that made the technology effective. The systems provided altitude capability, but crews had to exploit that capability through skilled operation. They climbed to assigned altitudes and maintained them despite fatigue, cold, and fear. They managed turbocharger systems through combat damage and emergencies. They completed missions that pushed human endurance limits in environments where equipment failure or pilot error meant death. The final verdict on turbocharging as a decisive World War II technology is written in the strategic outcomes it enabled. American bombers destroyed German industrial capacity systematically, reaching any target regardless of location or defenses. The altitude capability that turbochargers provided was central to this success. It allowed penetration to heavily defended targets. It reduced losses to manageable levels. It forced German fighters to operate at altitudes where their performance degraded catastrophically. The German decision in the 1930s to avoid turbocharging was reasonable given their doctrine and operational requirements. But it created path dependencies that couldn't be reversed when the war demanded capabilities those early decisions had foreclosed. The Luftwaffe spent the war trying to counter bombers operating at altitudes their fighters couldn't effectively reach, using technology they'd rejected as too complex a decade earlier. The Americans' willingness to embrace complexity, accept maintenance burdens, and commit to unproven technology created advantages that German engineering philosophy couldn't match within wartime constraints. The story of how exhaust-driven superchargers made B-17s untouchable at 30,000 feet is ultimately a story about different engineering cultures, different strategic visions, and different willingness to accept complexity in pursuit of capability. The Germans chose reliability and simplicity. The Americans chose performance and capability. Both choices were defensible, but in the context of strategic bombing doctrine, the American choice proved decisive. The turbochargers that German engineers had dismissed as impractical enabled operations that German fighters couldn't counter, creating altitude sanctuaries where American bombers operated with relative impunity, while systematically destroying the industrial capacity that sustained German war efforts. The mathematics were written in thermodynamic efficiency and pressure ratios, but the outcome was written in destroyed factories, depleted fighter forces, and the eventual collapse of German air defenses. The device that seemed too complex to work reliably proved reliable enough to change the strategic balance. The altitude capability that seemed unnecessary for bombers proved essential for survival, and the engineering decisions made in peaceful laboratories during the 1930s determined who controlled the skies over Europe in 1944, demonstrating that sometimes the most important battles are won years before the first shots are fired, by engineers pursuing solutions to problems that don't yet exist, but will define the limits of what's possible when the world burns.